Please send your homework papers to your left. They end up on that end of the room. I want to continue our investigation of the way probability works. We're talking about our complement idea on Friday, and we really based our idea, our behavior, on that Venn diagram. So let's consider looking at what happens when we have more than one event in the same sample space. So, if I'm working with more than one event in my sample space, what's my new Venn diagram going to look like? Okay, so each event is a circle inside the box that is our sample space. So if I've got more than one of them inside my given sample space S, I can have event A, and I can also have event B. But when I look at this, I don't know whether or not event A, event B, have any overlap at all. For example, let me go back to my standard deck of cards. I could ask you about event A being the chance that the card you draw is an ace. I could also ask, what's the chance the card you draw is a heart? If my events are ace for event A, heart for event B, do they have any overlap? What is it? Right. So I need to take into account possibilities of overlap when I look at these. If I want to talk about the idea of looking at one event or the other, when I talk about sets, we use the term union. Speak of A or B. On the other hand, when I want to talk about both of them happening, we write an intersection. Personally, I don't care if you use the union and intersection or if you just use the words or and and. What I need to think about with the or is the idea that it is inclusive. You can have one or the other or both. In terms of that Venn diagram, if I asked you to shade in A or B, what parts would you shade in? But that's exactly what I just said about the inclusive idea. Remember, we were talking about aces, hearts, or both, right? The word or here includes the option of both. So when I go to write A or B, the Venn diagram that I shade in actually covers all of it, including the part in the middle. Whereas if I said A and B, then I would get only the middle. Well, let's think about the way we count these. If I asked you, you pick a card from my standard deck, what's the chance it's an ace? Four out of 52. I love it. What's the chance that it's a heart? 13 out of 52. What's the chance that it's an ace or a heart? Why 16? The ace of hearts is in both of those things, isn't it? So instead of just saying, oh, well, I've got 4 chances to get an ace, 13 chances to get a heart, 13 and 4 is 17, I have to account for the fact that the ace of hearts is double counted here. So, when I do an or, there's a new counting rule. I have to count all the things in pile 1 plus all the things in pile 2, but then I have to take away anything I double count. But this is exactly this. It's the and between those two events. An ace and a heart, which means I can generalize this rule. I can say the chance of A or B is the chance of A plus the chance of B minus the chance of both. Happening at the same time. This and is called a joint probability. And we'll work on more ways for computing that as we go forward. Questions? A joint probability is always smaller than or equal to either of the simple probabilities it comes from. So P of A and B must be smaller than P of A or equal to it. P of A and B must be smaller than or equal to P of B as well. Why? Strictly from a Venn diagram issue. Why does this need to be smaller than either of those numbers? But not only is the area smaller, the overlap area is inside the circle A, isn't it? And the probability of A comes from the whole circle. Probability and only comes from the sliver. Same thing with B. It's got to be smaller because the simple probability is just one circle. And the joint probability is the overlap.
Is it the probability of A times?
No, it's just addition. It's only times in certain cases. Only times in certain cases. Let's see if we can figure out what that is. Promise, we'll get there. Because it depends on how the events relate to each other. I said here I had aces and I had hearts, right? They have some overlap. But if I multiplied those two together, I wouldn't always get 1 over 52. I wouldn't in this case, because there's something special about aces versus hearts. Figure out what that is. It is possible sometimes that there's no overlap at all. What if the two events we were picking at had nothing in common at all? For example, if A and B do not overlap at all, we call them mutually exclusive events. In craps, you roll 2 dice. If on your first roll you roll a 7 or an 11, you win. So, if my two events are I win on my first throw or I roll an even number, there's no overlap at all. And if that's the case, then our Venn diagram now looks different. In set terms, we would say that these are disjoint sets. Well, now, what's the probability of A and B? Zero. It's got to be zero. There's no area for me to look at. Well, that's going to make that calculation we were just doing a little easier. If this number is zero, there's nothing for me to subtract. If I have 2 or even more events, that when I take the or, I get the entire sample space, those are called collectively exhausting events. Just like our coin flip was either heads or tails, and those were the only chances. If I tell you to roll 1 die and I give you the options 1, 2, 3, or 4, 5, 6, that's an exhausting set. But I can also say, how about 1, 3, 2, 4, and 5, 6? That's also, but then it'd be a set of 3. That's okay. We will find, again, a use for all of these. Questions? You pick a card. I would like to know what the chance is that you picked a heart. You already know that number. Chance you picked a heart. 13 out of 52. But what if I give you more information? The card you picked is red. What's the chance you picked a heart? Why? The diamonds are also red. My chance now, instead of looking at all 52 cards, I only have to look at 26 cards. There are 13 diamonds and 13 hearts, and they're all reds. Okay, so what happens to our probability when we gain additional information? Now, this is called conditional probability. So, we write it like this, and we read that symbol, that vertical bar, as the probability of A given B. So I'm giving you more information. The example I just did said, what's the chance of you pulling a heart, that's our event A, given that I tell you the card is red? The picture that went with this one on page 162. Here, I'm no longer looking at the whole sample space. I'm only looking at what's going on within B. If I tell you the P of A given B, I'm really wanting to know how much of this circle is taken up by the overlap. It means I no longer care about the whole sample space. I only care about the part that is within B. Well, it turns out the way to calculate this, the probability of A given B is the probability of A and B over the probability of B. I'm really only measuring how much of the circle that is B is occupied by the intersection. Now, what this does is it changes our count. It changes our sample space. Originally, when I asked you what was the chance you drew a heart, heads just for coins, what's the chance you pulled a heart out of this deck? You told me 13 out of 52. Once I told you it was red, you got to take half the deck and throw it away. Only look at the red cards. That reduced our sample space from being the entire box only being this one subset already. Formally, I would say, oh, well, the chance of getting a heart is 13 out of 52. The chance of getting a red card is 26 out of 52. So formulaically, the chance of getting a heart, given that your card is already red, is the chance of getting a heart and red card over the chance of just getting a red card. But all the hearts are red, right? Whole suit is red. So how many ways can you get a red heart card? 13 out of 52, right? But we already said the chance of getting a red, 26 out of 52. And when you simplify those fractions, what do you do with the one on the bottom? Algebra was a long time ago, man. I can't get rid of the whole things. What do I get rid of? I cancel the over 52s. You take the fraction out of the bottom, rip it out, flip it over. So this would be 13 over 52 times 52 over 26. Those are gone. 13 out of 26. Knowing our card was already red changed the probability that we got a heart. Learning more information changed our probability. Let me go back to that formula for a second. Colin, you asked me about multiplying. To find P of A and B, right? But if we look at this formula right here, it turns out that my multiplication is a little different. If I rearrange this formula, it says that the chance of A and B is equal to the chance of A given B times the chance of B. There's the multiplication we want to do, but the first part isn't just P of A, it's the conditional probability. So this is different. There are two examples on page 163. The first of which talks about unemployment rates versus high school dropout rates. So here on page 163, I am told that of the population aged 16 to 21 not in college, 13.5% are unemployed at the time of the writing of the book. And 29.05% of those are high school dropouts, and 5.32 are an and. They're unemployed and high school dropouts. So if I tell you person X is a high school dropout, what's the chance they're unemployed? Probability of being unemployed, 0.135. The probability of being a high school dropout, 0.2905. Probability of being both, 0.0532. Using our formula, probability of being unemployed if you dropped out of high school is the probability and over the dropouts. In other words, we've reduced our sample only to the 29% of people that are already high school dropouts. And that's why the bottom of this fraction changes. So it turns out that that's 18.3%, which is a much larger number than the 0.53% or even the 13.5% that we knew about unemployment in the first place. So we have the conditional probability, 0.1831, versus the unconditional, 0.1350. But then this version allows me to multiply. Where's my problem for this? One about Spanish. Here we go. Problem 23. 62% of freshmen are taking a foreign language course. Of those freshmen taking a foreign language, 80% are taking Spanish. All right, let me read this carefully. Of the freshmen, 62% are taking a foreign language. The chance of somebody taking a language as a freshman is 62%. Of the people taking a foreign language, 80% are taking Spanish. How would I write the expression P of something for that? Of the freshmen taking a language, 80% taking Spanish. What is the probability? It's the probability something equals 0.8. What's the something in that sentence? Aha! The chance they are taking Spanish given that they are taking a language. That's the important statement. This is a conditional probability, the way they expressed it. Now, the question asks, if I walk up to any freshman, what's the chance they're taking Spanish? Notice that is an unconditional probability. Aha! Because that would be the chance that this person is taking Spanish and is taking a language. Because some of the freshmen don't take languages at all. That's an and. That's the formula right at the top of the screen. So that's exactly what I would do, is I would take the conditional probability of Spanish and language and multiply by the probability of a language. That's 0.80 times 0.62. Grab your calculators, give me a number. That would be 0.6 times 0.8. 0.496. So here, the idea that someone is taking Spanish or taking a foreign language at all, those ideas depend on each other. They're interrelated. If you're not taking Spanish, you could be taking a different foreign language. But if you're not taking a language, there's no way in hell you're taking Spanish. So we want to try and define this sort of relationship. So let's suppose I have two events, A and B. And the chance of A is not the same as the chance of A given B. Then I want to use the word dependent. That A and B are dependent events. Now, please note that is not cause and effect. We saw that being a heart and being red were dependent upon one another. The chance of having a heart was 13 out of 52. The chance of having a heart knowing your card is red was 13 out of 26. Very different numbers. But having a card be red doesn't force it to be a heart. On the other hand, if P of A does equal P of A given B, then knowing information about event B doesn't tell you anything extra about event A. We're going to say that these are independent events. Now, this turns out to be our definition for independent. So if I tell you that they're independent, that tells you that the conditional and the unconditional are the same. How does that affect our multiplication formula? Colin, here's the formula you wanted. When my events are independent, I can just multiply the individual probabilities, but only when my events are independent. What's the chance I roll a 2 on that die? You're mumbling. 1 out of 6. What's the chance I roll a 2 on this die? The same thing, right? 1 out of 6. So what's the chance I roll 2 2s? Does knowing anything about the white die, tell you anything about what's going to happen with the red die? They're independent of one another. So the chance of this happening and this happening is 1/6 times 1/6. There's no relation between them. There's no dependence. To that end, the game of Yahtzee is a probabilistic lifesaver. Because if you've got 5 dice and they don't talk to each other, right? So I know what's going on, each of them independently. And if I have more than 2 events, then this rule extends to as many independent events as we want. Question of the morning. Who gives a flying about this? Why do I care? What happened with Cloudflare a couple weeks ago? The entire internet went down because they pushed out an update and all of a sudden all sorts of servers crashed. So if you want access to your data, how many of you have stuff in the cloud right now? Where is it? The cloud? No. It's on someone else's computer somewhere. A cloud server is somebody else's computer in a building somewhere else. How many servers is your data on? Reliability is based on this idea. My computer will crash eventually. I'm not looking forward to it, but eventually my computer will crash. I make backups for precisely that reason. Let's suppose my computer is part of a server farm, and it's got a 1% chance of crashing. If your data is on that computer and it crashes, you have a 1% chance of losing everything in your data, right? But let's say I put your computer data on 2 of my servers. So the only way you can't get at your data is if both of those servers crash at the same time. Now, those servers are independent of one another. One of them could be down in Johnstown, one of them could be in Delaware. I actually have information on servers in Singapore and in Germany because Amazon Web Service puts their crap all over the world. So there's a 1% chance of your data disappearing off of one server. What if it's on 2 servers? What's the chance your data is gone? Well, there's a 1% chance of the first server going down. There's a 1% chance of the second server going down. So the chance of both of them crashing is the chance that the first one crashes and the second one crashes. But according to this formula up here, that's just multiplication. And so that is 0.01 times 0.01. What is that number? Which means there's a 99.999% chance your data is okay. Even though each individual server is only 99%, putting your information on 2 of them gives you 99.999% safety. What if I put it on 3 servers? Or 4 servers, or 5 servers? I could keep this going, right? Even if each individual server wasn't at 99%, let's say they were only at 97%, the more places your data is, the lower the chance of your data being vanished into the ether. Reliable, redundant data systems are the backbone of storing your business information securely. If you want to know where it is, how many servers does it have to be on for it to be safe in the cloud? Or even safe within your hard drive, within your system. The MacBooks don't have it, but a lot of large business computers have multiple hard drives within them. And they make multiple copies of the same information. They're called RAID, redundantly accessible independent devices, RAID arrays. Large backup computers, if you own a backup hard drive for your house, for your network. That's what's on there, multiple independent hard drives. And it's doing this so that if one of them goes down, you'll have others to catch stuff. Questions? Yes, I'm sweating through my shirt too. It sucks. So let's take our frequency idea, our frequency distributions, our probability ideas, and let's create something called a contingency table. A contingency table is like a two-variable frequency distribution. So instead of just looking at one outcome, we can look at two different things. The example in the text on page 170 deals with MBA students, their status as students, and their engagement in the program. A full-time student is taking classes full-time. A part-time student is taking classes part-time, and an executive course student is only taking a fixed evening course, either one or two at a time. Our MBA program here at Seton Hill is an executive MBA. Then we have student engagement. And that's either low or medium or high. And we can measure that by the frequency of forum posts or the grades they're getting or the number of times they email a professor in a given week or anything like that. We can sample all this sort of information. There are 360 students in the MBA program in our example. There are 9 possible categories based on which of the program types they're in, full-time, part-time, or executive, and their respective engagement levels. I'm going to put in the numbers here. This table appears on page 170. So how does this sort of a table help me? Well, I can think of these as like events A and B, right? So if I asked, what is the probability that a student is of low engagement? How would you answer that question? How do I know what the chance of a randomly selected student is of being low engagement? Look at the column, look at the total of the whole thing, right? That's called a marginal probability. I pick a whole row or a whole column, and I measure the numbers on the ends of the rows, the numbers on the bottoms of the columns against the whole thing. What is the chance that I have a student who is part-time? Remember, I randomly select a student here. What's the chance they're part-time? Exactly. These are marginal probabilities. Joint probability. Joint probability was the word and, right? What's the chance I've got a part-time student and low probability? Say again? Exactly. I'm just looking at this one cell, part-time and low engagement out of 360. So, how can I do conditional probability here? What's the chance that a student is low engagement given they are part-time? Aha. But we already know both of those numbers. We just worked them out. But how did you do it so fast? I can go back to my table and I say low part-time given part-time means really I only need to look at the part-time row. Ignore everything else. 64 of them are low out of a possible 88. I'm no longer looking across the whole table. A conditional probability restricts you to the row or the column for the given part. So rather than do the calculation this rate, I can say, oh, P of low given part-time is 64 out of 88. What about the other way around? What is P of part-time given low? How would I do that one? That's a number bigger than 1. And remember, all probabilities have to be between 0 and 1. So that can't be the right answer, unfortunately. This time, the given is the low, right? So instead of looking at this, I'm going to look at this. What's the chance if I tell you you're already low, you're restricted to the low column? What's the chance you're part-time? 64 out of 280 this time. So, by having a contingency table, I can do a lot more of these calculations a lot faster. And by the way, this allows me to check for independence very, very directly, doesn't it? More on this at our next class, but that is not Wednesday, because Wednesday is the test. The homework key will be posted in another 2 minutes. If you look at our calendar carefully, our next class is also not Friday. Why? See, you're supposed to look at the schedule, people. The schedule tells you that on Friday, there's a career fair. I won't be here. I'll be there. So our next class where we get to do more of these contingency tables is a week from today. I will see you all for the exam on Wednesday. Yes.
Log up that.